you talk about this stuff, you'll be on the internet tomorrow. Just have to warn you. Today I'm trying to do this on the cheap with a Rube Goldberg camera. So last two lectures we discussed how to write Feynman rules for quantum chromodynamics, and last lecture actually quantum chromodynamics. It's a special case of electrodynamics. But you know, once you know electrodynamics, quantum chromodynamics is you know, you're 2/3 there. You have to learn some group theory to write quantum chromodynamics Feynman diagrams. And we wrote our first diagram, and today we will actually try to evaluate the vertex correction to electromagnetic moment, or at least we'll get started on doing this. Schwinger correction. In parlance, that's called G minus 2. So G is what magnetic moment actually is, and 2 is what Dirac says it should be. So that's anomalous. This is not anomalous, but it seemed anomalous experimentally when it was first measured. Magnetic moment. And in the flash of brilliance, I've aimed the camera only at the first middle 2 sections. So this is off camera. So the diagram is, here comes an electron. She has mass and she has spin. And here comes a photon. Electron in. And out. And the first correction is electron emits a photon, a virtual photon, which is allowed by quantum mechanics, not allowed classically. And while the electron and photon coexist, both of them now of the mass shell, the electron scatters off a weak magnetic field, which we discussed last time, and recombines or reabsorbs the photon. So coming in, there is a momentum on mass shell, momentum P. Coming out, there is a momentum on mass shell, momentum K, and then there is photon or external classical magnetic field picks up a difference, and we'll be interested in limit when this difference goes to 0. That's a physical measurement of anomalous moment of electron. And that is a P minus K momentum flowing this way. And then there's a prime plus K flowing this way.
So is this a scattering?
Yeah, this is a scattering in a vanishingly small magnetic field, classical magnetic field. I mean, this is true for any scattering process of electrons. Usually, you know, when you think of scattering, you think that there's another particle, for example, a nucleus, and you compute some scattering cross-section. This is just a correction to spinning electron moving in a weak magnetic moment. So, last time we discussed the form of classical magnetic field and vector potential that encodes it. And we wrote the diagram in the Feynman gauge. So there is E squared for the two couplings here, and this E is absorbed into the definition of the vertex. I can multiply this by E on the side, and then I will have 3 powers of it. But the important ones are these that have to do with the virtual photon. And this is most conveniently computed in a momentum space. And the only thing that varies is the momentum of the photon. There is one internal degree of freedom that has to be summed over. And I'll break it up. So here I'm just following the I've looked at actually my first 3 papers which were on the subject, and it's extremely sophisticated. It's so sophisticated it's very hard to explain one loop correction, because I computed 3 loop corrections, that it's not worth your time to do it in an amazingly elegant way that I did it as a graduate student. So we'll do it in a pedestrian way. So there's a numerator and denominator. Numerator is a 4 vector because the vertex here is a photon carries Minkowski index. So the numerator has gamma mu from here.
Is the form cover side or
Thanks. Yeah.
The internal photon propagator is contributing a plus k to the electron on the right, right?
Yeah. And it's minus in.
Does it matter?
These 2 guys.
Yeah,
Yeah,
it matters
this is
for the
correct,
upper.
right?
It matters if the upper one is p prime times k.
Then it should be p prime minus k, right? On the left, and it's integrated over, so it doesn't.
Oh,
No, it is okay. I mean, they add up.
Okay.
So these 2 guys add up to that. And these are coming out, so they add up to that. So I think it's correct. So there is this photon vertex. The electron coupling is, electromagnetic coupling is in here. Then there is a propagator. The numerator part of the electron propagator, which is then there is external vertex, which we'll say is mu. This is the Dirac field, and then there is a P plus P plus M. And then there is G mu, because in the Feynman gauge we had a G mu u over k square minus there's numerator only has a Minkowski metric, which we have used here. So this is a numerator. And we will work it out in some detail. The next thing we have to work out is the denominator. And what we observe is that the denominator will have three things that depend on k squared. They'll be product of photon propagator, or there will be sort of Klein-Gordon propagator part, or the Dirac and Klein-Gordon part. So you'll have form of having three factors. And now what you have to notice, these factors are quadratic in k because they're all k squared, etc. And we're integrating over k squared. Now, if we could convert this into a Gaussian, we would be in heaven because we know how to evaluate Gaussians. That's about the only thing. And if you look at the links in the course, I've given you a link to a popular lecture by Witten, which was actually quite technical, but totally on level of this class, in which he explains what Feynman diagrams are. And he has a nice interpretation. So promoting this into a Gaussian is called Schwinger trick or something. But Witten has a nice interpretation of that trick once you get up in the Gaussian, and he really starts explaining that this very much looks like the integration, the path integrals that we've done before, and that there is a proper time in this. You can interpret the Laplace or transformation you did to make it Gaussian as a proper time. And it's very cute. And, that's his trick to get you into the string theory, because then he says, well, if it's not a particle, but it's a loop with a blah, blah, blah. But it's very nice. I like the interpretation. At this point, I'll just state it as an identity, which I guess I'll give it to you as a problem. So whenever you have a product of this kind, you can write it as an integral. That looks like this. So that's just an identity, and where these things actually have to be ordered, so the 0 runs from alpha, and beta runs from alpha, and gamma you can get rid of by just doing one integration, because you have one delta function to integrate over. So that's an uninteresting identity, but it's extremely helpful because you started with something that was momentum or space, etc., and you're able to bring it to a form where you have something over momenta squared, some quadratic form. And this kind of things we can integrate. And in the way that's done by Schwinger, and that's done in the, for example, articles that I've written with my advisor, I guess I should tell you about my advisor. So Toichiro Kinoshita survived the firebombing of Tokyo. So this was one of the great achievements of Second World War. It was a carpet bomb run by Curtis LeMay, the famous general from the Vietnam War. And it burned the Tokyo down. It was much more deadly than Hiroshima and Nagasaki. But Tom survived it and came to the United States. And he became a legend. He's a member of National Academy of Sciences because the man doesn't make errors. So it's totally scary. I worked with him for a number of years, and I've made some errors in our calculations. Not to Tom, she never makes errors. And this kind of calculations get very hard. I mean, there are thousands of diagrams, and you have to work for years to do it. So, Tom Kinoshita is made out of different stuff than the rest of us. Very impressive man. And, we have much more elegant way of computing this in general, which is related to graph theory and Kirchhoff currents and graphs, etc. But that would take weeks to explain, so it's not worth doing. So we'll just do a pedestrian version here. And so denominator, cube root, meaning just the thing that's there, has to remember where. Once I get rid of the gamma calculation, I have a delta alpha, delta beta calculation to do. So this is an integral in a plane, if you wish. And this one shows up as A3. I've just replaced gamma by 1 minus alpha beta, and that's why 1 shows up here, plus beta and 1. So what's in here, written in terms of K's and P's, is the denominator of this propagator here. So this K square comes from this replacement here. And this is just the Klein-Gordon kind of new denominator. And same here, this K square came from there. I need a 2. Thank you, Pavel. Let's see. It becomes K squared plus 2K dot, and these are 4 vectors, so this is a 4 vector dot. So I don't have to write in this, but that's what it means. Let's see. So when you square this, you get a cross term 2k dot p prime alpha, and k squared cancels. Same story here. So that's why alpha and beta don't have k squares. Then p prime squared, this is a mass shell momentum, so that cancels this m squared. And p squared is a mass shell momentum, so that cancels this m squared. So you get a very simple expression, which you can obviously complete a square of because it's quadratic in k, and you will, in this integral, I still have to do my integral over k. This integral, I'm just working on the denominator right now. So now complete the square. We write L mu to be A mu.
Is this denominator is what we have in vertex?
No, we just, this is denominator, now we're just evaluating denominator, because it's cube, I'm writing a cube of denominator.
Okay. So denominator of identity.
Denominator of identity?
You've given up that because it's not exactly what we know. I'm confused.
We will have
D,
alpha and beta.
Yeah, where are the alpha?
okay, let me write D in detail. But D is k squared from here. No, well, D is the three denominators. First one is P slash plus pk, no slash, square minus m square. The second one is p plus k square minus m square, and the fourth one just gets k square. And here I've used that the denominator, the propagator has a form, p square minus m square plus I epsilon. And it turns out we won't have to worry about I epsilons in this calculation. And the way we got it is that we multiply the inverse of the spinor propagator plus, so we get this slashes here.
My question is, where are integrations over alpha and beta in this expression you're writing?
The identity says that you can write this as triple integral, totally symmetric, but it satisfies one Dirac delta condition. So I use it to get rid of gamma. So that's how I got there. And it has to be in a sort of a trapezoidal area.
And the one before, below that, d to the 1/3.
Yeah.
Where are alpha beta integrals?
This is just, oh, I see.
It's just the denominator.
No, I'm sorry, just denominator.
Yeah, right.
Yeah. You're right. The integrals are still there, but denominator.
In front of beta, the denominator over there.
What about the beta?
A2 minus A3. You have it written as A1 minus should be A2.
Absolutely. So it simplifies. The next thing we do is we can complete the square. because we'll have the integral here over, before the k it's from plus to minus infinity, so we're allowed to shift the origin as we wish. It doesn't change the integral. So shifting the origin of the integral by alpha p prime u plus beta p u is what we need to complete the square. So if you square this quantity in this variable, it will be 4 momentum L square plus alpha plus beta square. And every time we square these guys, we get m, because they're on the mesh, all m square. So we get a very simple expression for the numerator of this integral. So the only thing that remains is to do the integration over the momentum of the photon in the shifted coordinate. So let's leave this aside, and I will erase all of the stuff except the last result. And focus on the denominator, on the numerator. So, after I did this calculation with my advisor, in the career afterwards, I had the wonderful opportunity to talk to C.N. Yang, the great theorist, quantum field theorist, and originator of Young-Mills theory, one of the originators. It was already done before by Klein, etc., but it doesn't matter. And every time I talk to him, it will be always the same conversation. They have shown, Young and Mills have written 2 papers. So there's Mills and Young and Young's and Mills. And Mills and Young paper is that they've shown that when you do perturbation theory at the 3-loop level, there is one diagram in which there is an ambiguity about routing momenta through the diagram. Now, the way this theory is actually done, if you do calculations, is there is a totally general way of getting rid of momenta, and everything is written in terms of these integrals, alpha, beta, gamma, that are done, and they only depend on topology of the graph. So no momenta are routed. So every time I have the same conversation, says, yes, Professor Young, but blah, blah. And 5 years later we meet. He says, well, in 3-loop diagrams, there is an ambiguity because this diagram we showed in that paper in 1955 or something. And there is no ambiguity. The theory is beautiful. And it's, it's a whole new ballgame. Once you start thinking seriously about Feynman diagrams, which I don't recommend, but you can get a Fields Medal, so Kontsevich, at the Institute for ESGS in Bursirvet in France, has it for that kind of thing. They're beautiful conjectures. They're related to polylogarithms and there are all kinds of beautiful things it can do. And they become a subject of their own. But for us, they're only a crutch because that's the only way we know how to compute quantum field theory, and I think it's another smart way to do it. But that's the only thing we know currently. So let me go to this guy, and we write this, we have changed, I've erased transformation of k to this new variable L, shifted variable. So, you know, this is something that has to do with loop, and I'm free to redefine as I wish. You know, this is Marshall external, and that I cannot mess with. But we have just, we can now rewrite P by, I guess I better write again the transformation I just, so use the new momentum, internal momentum, as the original momentum plus the thing now that depends on our reparameterization of momentum. So it depends on that. So if I substitute that inside, then my P's will change. So I will get, this will become L, but this will become P prime U, this 1 minus alpha. Use the slash notation just for the heck of it. Minus P.
What did you do to get the velocity?
What I did is in bringing the denominator in convenient form for integration, I shifted my internal integration K. I shifted it to have a new origin. I added some components from the external momentum, and that's totally legal because I'm allowed to change the origin of integration as I wish. And the Jacobian of the transformation, it's a linear transformation, so Jacobian is 1. So that's why we're suddenly having things that depend on alpha and beta also in numerator, because that's what we did in denominator. We redefined this integral to be integral over L. Shifted variance. Okay?
So, where I should if you want to write equal not replace. So on the left you have old variables, on the right new ones.
It's the same numerator.
Okay.
Anyway, Powell objects whether this thing depends on K explicitly, and he doesn't like that now it depends on L explicitly without being called something else. You might be right. As my wife tells me, you might well be right, which means she doesn't really believe it. A very polite way of saying it. So now we'll do some Hund, which is essentially what we want to do. This is, as written, this is now a general vertex, and it's a part of one loop corrections to electron photon vertex. There are two other terms we ignored because they're not one particle reducible. But all of them have to be put together to define a renormalized field theory, which I'm skirting around, but it looks like we'll have some time to do renormalization. after Thanksgiving, so it's not always lost. So now the next step of manipulation will be just to isolate the magnetic moment part of this vertex, because this vertex corresponds to so-called charge renormalization, or just strength of a charge, and it has a contribution which is proportional to this sigma mu nu, to the angular momentum, or spin angular momentum term. So we'll just try to isolate that term, and that we'll do by using Klein-Gordon identities as before. So Gordon decomposition. When we look at the vertex in P prime and spin out, so what this means is you have matrix element. If you're thinking in all quantum mechanics, spin can be up and down for a fermion. So you have matrix elements that say that external field can actually flip the spin, so that's why S should be written in. And then the G mu nu, just this vertex by itself, could be written in terms of P mu plus P mu N. So we derived that last time. And this is the commutator of two-dimensional matrices, which describes the coupling of magnetic moment of electron, this external momentum. And this we also did last time. Then we can write the form factor. So the general thing of this one particle reducible guy. Let's just call it form factor. If we have corrections to any order, they would contribute P prime minus P is called Q in this formula. So using Gordon decomposition, we can trade between having either gamma matrix in the vertex or having this form in the vertex. And we can associate the magnetic moment term with having a momenta in the vertex. Has to do with magnetic moment. Let me just check my notes from last week. Did I really value this one? Okay, so what I wrote last week, something that made eminent sense. You have all possible one-particle reducible corrections. So photon in, electron in, electron out. And evaluate on the mesh shell. And this is P momentum in, P prime out, and momentum in. So, one particle irreducible free vertex. That's one IE. So that's the bare vertex version. And then all corrections that contribute to the vertex, gamma vertex over square. They can be interpreted as charge renormalization plus I sigma mu mu q mu qm square. And in experimental measurement of charge, you're interested in charge just in a static electric field, so you don't impart momentum to it. So renormalize or physical charge. Is the bare one times everything that quantum mechanics, quantum field theory brings, evaluated at zero external momentum. And this guy, F2, evaluated zero. We did it last time. It's interpreted as anomalous magnetic moment. So the way this thing works out is that the Dirac prediction from relativistic physics for magnetic moment works. There is no renormalization for that guy. Once you fix the physical charge, it's absorbed in that. That gives us, one in this, in some formula which I'm writing here, I guess. And Schwinger anomaly is the difference between quantum mechanics and Dirac relativistic. Quantum field theory, Dirac relativistic quantum mechanics. So now I did a little bit of this using the Gordon decomposition to bring it to this form. And that's just convenient for calculation to have the anomalous magnetic moment associated with momenta up there. As you will see, this is very handy because this integral looks like it's logarithmically divergent because it's something of order 4 integrated, and the denominator had a power 4. Looks like power 6. Okay, let's just go with it. So now we are not interested in this is not a very persuasive argument, so we're not interested in stuff that renormalizes the charge. That's for somebody else to worry about. So we'll drop anything that has to do with gamma mu, and we'll only look at this part of the denominator. And here is the denominator, so let's work it out. So first thing we notice is that we have a very simple term, and this is a constant, and this is a constant, right? So there'll be term will be G mu, you know, this thing, this gamma in the middle sandwiched by another gamma, and this is of order m, and so there'll be term here. So the term that will look like m squared gamma mu, and we know that that thing is, if you work it out, that's proportional, and I think we worked it out, it's proportional to gamma mu. So we'll draw that. That belongs to this part of the calculation. So that's this part to draw. I'll write down on here. We draw it. Then the terms of the following form. Maybe I'll have to write it in. I think I write mu again, but just in terms of L's. Then, you know, I'm integrating on d4k, forget the change thing for a moment. And if I pick up k from here and m from here, so I look at the cross terms of this kind. Then I have an integral which is odd in the powers of k. This is odd in k. If I integrate over all space an odd function, I get 0. So I can get rid of that one, then of course there's another cross term like that one. All right. Then I'll have terms that look like So that will be the terms when I that slashes again. So that's this term here, the cross term. Now, if mu and nu are different, then integrating this is odd in each one of them, so it vanishes. So I can get only non-vanishing contribution if they're the same. And you can easily show that this is 1/4 integral of d4k k square g mu nu. That's the only symmetric tensor we have available. Then there are terms which are linear in M. That means I pick up M factor and then I pick up factor of this on the other side. So they look like M gamma mu P slash as an example. So not momentum, but in external momentum. P slash from here, and gamma nu from here, and here I got an M from here, so that is and to evaluate those terms, I really don't remember, what gamma gymnastics I asked you to do in the exercises, but did I ask you to evaluate gamma mu slash A slash B gamma mu? Was that part of the problem? So it's, just the standard, these are gamma matrices, you use the anti-commutator relation of Dirac, you pick up G and U, and you work a little bit, and you realize this has to be a scalar number. And what scalar can you make from A 4 vector and B 4 vector? And after a little calculation, which I don't want to do now, we get minus 4 dot A dot B. Now, I can write it in covariant notation.
You should have both the same.
Yeah, of course. Thank you. Summed over the external limits. So, it looks credible because if you have two vectors, what scalar quantity can you form from them except the dot product? There's nothing else to do, and you have to compute the factor is -4. So that's standard Dirac gamma gymnastics. So if I put that in here, let's see. So I have two cross terms like that. Because there's also a term, this is probably T slash
Should be
gamma, this should be gamma mu, this should be gamma mu summed over two indices, and this is mu upstairs. And then there is also a term that looks like gamma T slash. That's this guy picking up mass from here. So, 1, 2, 3, 4. They have 4 gamma matrices in this form, so we use this twice. And again, I don't think, can I really do honest upper? What you want to do is you want to anti-commute one of these guys because you want to bring this to the form where you're looking at. Let me write it for you so I'll see whether you believe it. 4 and 1 plus this alpha So I use, I hope I didn't drop it, I use this identity here because I'll be integrating over L and not K to shift the origin. And what the identity does is it, when I replace
Why not you do this over?
let me just write it. No, I'm in deep waters right now. Let me just write it. What I need to write, and then we go and discuss it. Also, what did you ask?
Why I'm dropping over?
Why am I dropping which term? Because if I have a term that's proportional to L mu, it's linear and integral space. It's an odd function that's being integrated over all space. So anything that's proportional to K or L to the first or third power will drop out. I have to select this. So this is in the original integration. Oh, yeah, what I'm dropping is there are also terms that look like P, right? There's also these terms, M times K. So every time I write this, there's also a term that has a K here. Or in change coordinates, it will give me a lambda. And that one is odd. So this is just odd. So maybe, let me say, before here, actually, maybe it's easier to understand. Drop, here I've dropped terms proportional to K. It's a distance. Now, one thing I can't remember is why did I get a 2 here? So, I'll pick up a 2 when I do an anti-commutator, because I want to bring these guys together, p's and slashes, mu's. Is this what I need? Let's look at all this. So I have a P slash gamma u gamma set. So that's first term has this format, right? Lambda of gamma u, let me put it downstairs. Gamma u, gamma lambda gamma u gamma u. Agree? Algebra, okay. And I really didn't ask you to do this. Okay. Then we commute these two guys, so we get 2g mu u minus gamma mu gamma u. So this is e lambda times gamma lambda minus G multiplied. I hate this. Do I have your blessing? And I said, this one I asked to evaluate, or I did it in the class. So what's the answer for this one? This combination. No answer. Okay. It's too painful. Yes, gamma lambda. Lambda G2 is gamma mu gamma.
There's a two.
Yeah, it's gamma. There was a 2 here, 2 times minus
Yeah.
gamma squared gamma mu. This is 1, right? So it's, this is 2. What is it?
No, I mean, each gamma square. Maybe you are.
Yeah, what is gamma squared?
One.
No, 4.
Four.
4. 1. 1 or 4? It's a matrix. I hope it's 1, but you have to help me with that. I mean, that was the first thing. That's how I introduced it. So I thought we introduced it to be 1. So that's gamma mu. It looks to me wrong, but if this is 1, I subtract. Am I wrong? Hello. Anybody there? I'm off the blood. It's embarrassing. What is it?
Is gamma squared a sum? Over all four gamma
Sum.
matrices?
Yeah, you know, gamma mu, gamma mu. Looks to me like 4.
Or I.
And depend, I wouldn't believe in I. I think it's, well, let's make it 4. 4 times identity matrix. Yeah, okay. So if that's right, then that looks correct to me. It's minus 2. I mean, that I remember. Yeah, that feels right. Anyway, so you do this stuff and you prove this identity, you stick it in there. And so I think this 2 alpha came from, this 2 bothers me a lot because there was no 2 here. And I hope it came from that identity. We dropped that, but there was something. So then there is finally a term that has no m in it. So that's a term where we're multiplying these parts together. And we know that cross terms where there's a k here and p there will vanish because they're odd by integration. And k squared term, let's cross that bridge, but there is certainly a term that looks like this. T slash I gamma u. So it has gamma ray. So I actually wrote an algebraic language. So what happened to me is in those days we didn't, I mean, this calculation was actually the reason why Stephen Wolfram decided to write an algebraic calculation, because he was a high energy physicist before he became benefactor of you all who are using Mathematica. And so in those days, the only computer I was allowed to use was in Brookhaven. I was in Cornell, but we had a synchrotron, and at night they allowed me to edit my files on the DEC 10s. So I wrote an algebraic evaluation language in the editor, so whenever they checked what I was doing, I was just editing. I was running Tico editor, but actually I was doing very gruesome calculations, of which this is a trivial part, because by the time you get to the 3 loops, these guys get endless, and you have to evaluate them all. But here is the worst in this particular calculation. So yes, it's exercises for you because it can be done. You can move this through using anti-commutations. And by the way, this is why Klein and Nishina, it took them months to do this calculation, because Klein-Nishina formula was formulas simpler than this, but it was scattering of external thing. We had lots of gamma matrices in it, and they only knew that they were 4x4 matrices. So they would multiply every day, every morning they would multiply 4x4 matrices, and they had 4 of each, because it was summed over. There were Pauli matrices stuck in the way that we did originally. So the original calculations are just crazy, but once you understand its algebra, it's very easy to automatize. And claim is that that's what this calculation is. And it's a little bit unfortunate. You notice that P and P prime have gotten interchanged, but you're sandwiching between U of P prime and U bar of P prime and U. So this one, which is gamma mu, which you can draw.
I don't like the indices.
What about the indices?
You have 30 mu's on the left-hand side.
This one is a mu. Again, when I do these calculations, I only draw pictures. So there is no confusion about things. But at this level, it's simpler to do it with indices. So then, you have to commute them back, so you can use the mesh shell property. And when this is all done, the claim is I'm sorry, but it's your problem set. So I will skate through part of this madness, and that after you have done all this stuff, you finally have a part of numerator that contributes to the magnetic moment, which is fine. this a lot. In high energy physics, there is a popular phrase which says blah, blah, blah. After some algebra, we obtain blah, blah, blah. And this after some algebra often turns out to be a month of algebra, but here it's only a few hours of algebra that you can do yourself. And we get that formula for the magnetic anomaly, second form factor at 0, which is minus I squared integral of d alpha d beta, from 0 to 1, and then the sum of them has to be 1, or less than 1. And we had a very simple numerator, which is 4 momentum square I still haven't integrated the momentum, so this is called parametric integral. What do you say?
Feynman parameterization.
Yeah, so this one is called Feynman. I prefer Schwinger, but the Laplace transform, which are they're the same. But if you listen to Witt and explain the Schwinger representation, it's more insightful. Put some physics in there. The link is on the web page. So the numerator is just quadratic in the 4 momentum. And this integral is another reason, integrals like this was another reason why Wolfram decided to develop the language, because he wanted to get rid of, the way we do this integral is we look up at Grudstein and Griesbach tables in the old days. But he wanted to compute it to do the lookup. So that's where Mathematica, originally Maxima came from. So to the cube, so that was an amazing simplification downstairs. And upstairs turns out also pretty amazing. You get alpha plus beta, 1 minus alpha plus beta. And that's the integral for the form factor after you do all the algebra. Now, the momentum thing you sort of know how to do, because this looks like the radius of something, so integrate the volume of some sphere, because it's radially invariant. So it becomes a one-dimensional integral in this radius, and multiplied by some combination of pi's that give you the volume of a sphere and gamma functions, which don't look like anything much. So once you do that integral, it turns out that integral here looks very special. But we know how to do this integral for every Feynman diagram. We know how to rewrite every Feynman diagram in parametric form. So there's a beautiful theory of how to do it. It's, graph theory of the same kind that's used in electrical engineering, actually, and computer science. And then you end up with this two-dimensional integral. And this thing here gave you minus I integrating this 32 pi square alpha plus theta here. Times the numerator that you already have. cancellation, and you get minus on these two i's, except it's a very important sign, and I'm not sure why it's not plus or minus, but let's say you trust me. And this is integrated in the alpha beta planes. It's integrated over triangle. So this is 1, 0. This is alpha beta. So if you first integrate in alpha, you're allowed to take any value, but then beta is limited to the vertical part. And this becomes 1/2 e squared 2pi squared. And this is the Schwinger correction. It was reported as half a page of physical review, basically stating that's the answer. And you will, get all the signs right in the exercise. But that outlines the calculation. You have to do some gamma mu gymnastics. You have to throw everything that doesn't contribute to sigma mu term in your calculations. You go to parametric representation. As far as I know, this is the best way of doing this integral. I don't know of better alternatives. And the result is very simple, because this combination is called alpha, fine structure constant. Then Schwinger was very pleased with this himself because this explained the current experimental measurement in 1948. So that was the first triumph of real quantum field theory, unabashed, full stuff. And it's a perturbation set. So then you should be computing also terms that look like that. Second order, there's a bunch of diagrams, not very many, that look like that. And the first calculation was actually wrong. So, first people who computed it made some errors. So it had to be fixed. And if you ever read Schwinger has written 2 books called Fields and Sources. And in the second book, he actually does it analytically. It's totally amazing. He does a 2-loop calculation. This calculation that I screwed up for you in the first loop, he does analytically there. And today, by the time you get to 3 of these guys, it gets really complicated. So, there are 712 basic diagrams. No, that's nothing, that's beginner stuff, because each one of them hundreds of terms, etc. So you're working with few thousand diagrams. People have pushed it now, have completed Kinoshita, the amazing advisor of mine, and his collaborators completed 4-loop correction. That took maybe a decade to do. Maybe I'm not being fair, and much of the 5th order is also 5 loops is computed, not all of it, but much of it. And what happened to us, while I was doing my calculation, the experiment came in, it was 3 orders of magnitude better than the result they had by that time. So theorists had to compute these corrections because experiments are so amazing. So I think it's one of the best finest thing that's measured in nature, this electromagnetic moment. And one possibility is that if you believe quantum electrodynamics, you might use it as a standard for alpha, for charge. And that's not obvious. You should do, because by the time you get to these higher order corrections, you start completing this polarization of photon into hadrons. So it turns out the way that higher order corrections are computed is that there's contribution that's measured at slack. So you measure at very high energy, you measure photon-photon collisions, and that goes by dispersion relations into calculation of magnetic moments. So this totally crazy thing, a ball and electron running around for months is measuring things you measure at slack, not large, not in CERN, but still, it's many GeVs that are contributing. Okay, that's it, and do the homework. Can you do the exchange? Hand me the homework for number 12 and
11 are graded.
yeah, 11 graded and 12